Hello, everyone. Welcome to section 13.3. In this section, we're going to be talking about tangent lines and derivatives. And in this topic, we will be using the ideas from limits that we've covered in the previous sections. But before we jump into that, let's start off by talking about a topic we saw a while ago. Let's remember average rate of change. So recall the average rate of change of some function, f of x, right? Between x and a is, so the average rate of change between those 2 points would be f of x minus f of a over x minus a. I think the formula that we were using in previous chapters was with a and b, but I mean, those just are arbitrary numbers, so we'll just use x and a. Same sort of idea. This is the average rate of change, right? Let's go ahead and look at this on a graph again. So graphically, if we're to look at a graph of maybe like a parabola, maybe something like this. I'm actually going to make this a nice color. Okay. Let's say that our x was here, for example, and our a was here. So that's kind of like right here, right here. The average rate of change is the slope of the line connecting those 2 points. Okay, so that's what average rate of change looks like pictorially. But what if we were to take x, this x right here, and we were going to slide it closer to a? So we can draw a picture of what that would look like if we did that. So our a was like maybe about right here. So if we were to take x and sort of move it from where it was originally, kind of down the line, closer and closer to a. Let's see. Our first line kind of looks like this. Our second line kind of looks like this. And then maybe it gets like this. And then maybe it also does that. And so you can see as this green bead right here, 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 here. So as the green bead slides closer and closer to A, we get a line that gets kind of closer and closer to something that kind of just barely touches. Okay. So eventually, we get a tangent line of our function f of x at x equals a. So let's draw one more picture so we can see it cleaned up. If we look at our parabola, oops, that line that was just barely touching at a, oops, boink, it just kind of touches the blue graph at that spot and nowhere else. That's the tangent line, okay? So a tangent line is a line that just touches the graph in one spot but doesn't cross it. Okay, so this right here is our tangent line. Okay, so the slope of this tangent line, because remember the slope of the lines leading up to the tangent line as we slid the bead, those are like the average rates of change between x as we slid it closer to a and a, right? So the slope of this tangent line, when they finally boink, meet in the middle, that slope is the instantaneous rate of change. And it's for f of x at x equals a. Okay. Algebraically, if we wanted to sort of write down this idea with a math equation, the idea of like sliding x closer and closer to a is a limit, right? So we're going to take the limit as x goes to a, right? Because we're taking a and we're making it really, really close to, or sorry, we're taking x and we're making it really, really close to a. And it's going to be the limit of the average rate of change. Now, some of you may have seen this before. This is called the derivative of f of x at a, which is denoted f prime of a. So this is the derivative. It's the idea of instantaneous rate of change of some function at a point. Equivalently, there's a sort of a second definition of the derivative of f of x at a point. This one's actually a little bit more common, but it's a little more mysterious as to where it comes from. You can get between them using kind of like a substitution. But most people use this formulation. So it's the limit as h goes to 0 of f of a plus h minus f of a over h. So this is more common. But both are valid. Both work. Okay. Well, let's go ahead and look at some examples of finding derivatives. I'm going to go ahead and use the second definition of a derivative just because it is more common, and it turns out that it's a little bit easier to work with as well for most things. So let's say we wanted to find the derivative of f of x equals maybe something like 2 minus 3x squared. Now let's say we wanted to find it at x equals 3. So we're going to do this using that limit definition above. So we want to find f prime of 3. So we want to look at the limit as h goes to 0 of f, so f of a plus h minus f a over h. In this case, our a is going to be 3, so this is going to be f of 3 plus h minus f of 3 all over h. Okay, so now let's go ahead and plug those things into the function. So we get the limit as h goes to 0. And so f of 3 plus h is going to be 2 minus 3 times 3 plus h squared minus f of 3, which is going to be 2 minus 3 times 3 squared. So plugging in 3. That's going to be still all over h. And then see if we can simplify this a little bit. We get 2 minus 3 times, and if we do 3 plus h squared, you can FOIL that out, and I think you get 9 plus 6h plus h squared minus 2, and then don't forget to distribute that negative sign in there. That's going to be minus 3 times 3 is 9 times 3 is 27. So that's going to be plus 27 over h. Okay, notice that I can cancel out this 2 and this 2. So I'm going to go ahead and do that in the next line. So if the limit as h goes to 0. And then I'm going to go ahead and distribute that negative 3 into the parentheses. So they get negative 3 times 9, this will be negative 27. Minus 3 times 6 is 18h minus 3h squared plus 27 over h. Okay, and now I can cancel these 27s, and I'm just left with negative 18h minus 3h squared over h. Okay, now I'm going to go ahead and factor out that common factor of h from the numerator from the top there. And we get h times negative 18 minus 3h over h. And now, the magic step, we can cancel these h's. And so we get the limit as h goes to 0, negative 18 minus 3h. Now this is just a polynomial in h. So we can go ahead and just plug in 0 for h here now. And then when we do that, I think we get negative 18 minus 0, so that's going to be negative 18. And hey, that's the derivative of that function at that point. So negative 18 is the derivative of 2 minus 3x squared at x equals 3. Okay, cool. That example is fairly straightforward. Let's go ahead and take a look at something that might be a little more complicated. So let's say we want to find the derivative of, and let's say it's going to be f of x equals 1 over the square root of x. A little bit funky. At, let's just do x equals 4. So we want to find f prime of 4. I'm going to go ahead and use the same limit characterization of derivative as I did in the previous example. So this could be the limit as h goes to 0 of f of 4 plus h minus f of 4 over h. Okay, so now we're going to plug those in. So we get the limit as h goes to 0. So this is going to be 1 over the square root of 4 plus h minus 1 over the square root of 4 over h. Now I'm going to do something that might seem a little strange in this next line. I'm going to go ahead and remember that the square root of 1 is just equal to 1, right? So secretly here, we have the square root of 1 over square root of 4 plus h, right? Because square root of 1 is equal to 1. And so we can pull out the square root as 1 over 4 plus h. And then we can do a very similar thing for that one as well. And so we can rewrite this as the square root of 1 over 4 plus h minus the square root of 1/4. Now it seems like, why would I want to do that? That seems very strange. But the reason I want to do it is because now, if you ever have square roots like this in a limit, especially a derivative limit like this, what we can do is we can rationalize the numerator. And what that'll end up doing for us is eventually we'll be able to cancel out that h on the bottom. So to rationalize the numerator, we're going to multiply it by, on top and bottom, square root of 1 over 4 plus h plus the square root of 1/4 over the same thing, like that. Okay, and then if we FOIL that out, we get square root of 1 over 4 plus h times square root of 1 over 4 plus h. So that's going to be the square root of 1 over 4 plus h squared, right? So this cancel out. We just get 1 over 4 plus h. And then when we do this, square root of 1 over 4 plus h times square root of 1/4. And then this will be minus the square root of 1 over 4 plus h times the square root of 1/4. So we're just adding, subtracting the same thing. So that's going to be 0. But let me go ahead and write that out so we don't get too confused. So this will be plus the square root 1/4 times square root 1 over 4 plus h minus the square root 1/4 times square root 1 over 4 plus h. And then minus square root of 1/4 squared. So this could be minus 1/4 over h times this. Same thing. Okay. So now these cancel out and we're left with the limit as h goes to 0 of 1/4, or sorry, 1 over 4 plus h minus 1/4 all over h times square root of those things. Okay. Now I'm going to go ahead and combine the fractions. I'm going to do that fraction subtraction in the numerator. I got distracted there by fraction subtraction. It's a fun little rhyme. Okay, so I think we need a factor of 4 on this one minus a factor of 4 plus h. Yeah, on that one. Over the same thing again. Looking pretty messy, but let's keep going. Let's go ahead and do that fraction subtraction. So we get 4 minus 4 minus h, don't forget to distribute that minus sign appropriately, over 4 times 4 plus h, all over h times square root of 4 plus h plus square root of 1/4. Okay. Now we see that these two 4s cancel out. And so we just have the limit as h goes to 0 of negative h over 4 times 4 plus h all over h 1 over 4 plus h square root plus square root of 1/4. Okay, so now I'm going to go ahead and rewrite this strange compound fraction as just a single fraction. And so technically this is the fraction negative h over 4 times 4 plus h. That's divided by this thing, right? And so if we do our fraction division appropriately, thinking of that as this thing as over 1, then I think we get minus h over 4 times 4 plus h times h times the square root. Oops, it's very long. 1 over 4 plus h plus 1/4. Okay. So now all that work was so that we could do this. Cancel those h's. And then we're left with the limit as h goes to 0, negative 1 over 4 times 4 plus h times the square root of 1 plus h plus, I'm gonna rewrite this, or actually I'll just leave it as square root of 1/4. Okay, so now we can start using some limit laws to break this up, right? So I'm gonna go ahead and break it up like this. I'm going to have, it's gonna be negative 1 over 4 plus h times 1 square root 1 4 plus h plus the square root of 1/4. Okay, and so then using one of our limit laws, we can break this up. So this is the limit as h goes to 0 of -1 over 4 times 4 plus h times the limit as h goes to 0 of this thing, 1 over 4 plus h plus 1/4. Okay, now this thing here, that's just a rational function, right? That -1 over 4 times 4 plus h. And note that 0 is indeed in the domain, right? Because we plug in 0 for h, we're not going to get 0 on the bottom. So we're okay. So we can go ahead and just actually evaluate this limit as -1 over 4 times 4 plus 0 times, okay, so for this limit, a little bit trickier, but I think we can break it up to top and bottom using another limit law, because I think that when we go ahead and do this, the limit of the denominator is not going to be 0, so we'll be okay. So this is the limit as h goes to 0, 1 over the limit of the square root, well, the limit as h goes to 0 of the square root of 1 over 4 plus h plus 1/4, the square root of 1/4. Okay, and now this thing that we evaluated before, I think that becomes -1 over 4 times 4, so that's -1 over 16 times, okay, the limit is h goes to 0, just 1. That's one of our special limits. That's just going to be 1 over, and then we can sort of break up this limit across the subtraction, and we can move it inside the square root using two of our limit laws simultaneously. So this will be the square root of the limit as h goes to 0 of 1 over 4 plus h plus square root of the limit as h goes to 0 of 1/4. Okay, so this can be -1/16 times 1 over the square root. Okay, so the limit of as h goes to 0 of 1 over 4 plus h. 0 is in the domain of that rational function, right? Because you plug in 0 for h, we get 1/4. So we can go ahead and do that. So we get square root of 1/4 plus square root, and the limit as h goes to 0 of 1/4 should be 1/4. Okay, so then we get -1/16 times, let's see, 1 over, I'm going to go ahead and rewrite this as, since we've got the square root of 1 over the square root of 4 plus square root of 1 over the square root of 4 equals -1/16, 1 over 2 plus 1 over 2, 1/2 plus 1/2. That's just 1 to 1 over 1, and that's just 1. So we get -1/16. Okay, so some of these derivative calculations can get a little messy and hairy, but if you stick with it and just keep chipping away, eventually something usually pops out. All right, go ahead and keep cracking away at that homework. And as always, let me know if you have any questions.